The topic of this talk is going to be simply secure tools for automated generation and evaluation of protected hardware. To explain you what I actually did during the last almost 15 years, I would like to give you an overview of what I'm doing. But beforehand, I would like to acknowledge these wonderful researchers who helped me a lot. These projects, they are mainly postdoc and PhD students in Bochum. Good. First, let me to give you a big picture of what I'm doing. It might be very, very abstract about the security. Yeah, I know that two people want to communicate with each other. Yeah, you have heard this story a lot, Alice and Bob, and then confidentiality that someone is between should not understand what these people are telling each other, and then you need some encryption function and decryption function. Yeah, I mean, it's symmetric cryptography. That's simple. Yeah, and then if we just call this security, of course, security is not only this, yeah. But if you call this security, many researchers are actually working in the math department and also computer science department. What they are doing, they are trying to design some cryptographic primitives, you know, like the ciphers, like symmetric, asymmetric, hash functions, and so on. Yeah, some primitives. And some other researchers try to do analysis, means that they try to understand whether this primitives which have been developed or constructed, they are actually doing well or not. I mean, checking the security arguments and security claims of the authors. Yeah. At the end, we will have a bunch of security primitives or cryptographic primitives that they are actually fine. What does it mean fine? I mean, they are secure under defined adversary model, because we need to define adversary model, and under this adversary model, then we can prove the security or try to prove the security. And at the end, we have a couple of these schemes that they are okay with respect to that adversary model. But okay, that's good. But why do we need this? Because we want to use them, right, in different applications. And then some of these applications are based on PC, computer, personal computers, and then there are many different topics of research, like network security, internet security, malware security, email security, whatsoever. Yeah. And then some other applications are actually embedded. You may ask, what are the embedded applications? I guess you can imagine that the devices that you are carrying with yourself every day, like the key fobs of the cars, like electronic passport or the ID cards, or your mobile phone, or set-top boxes that you have at home, like the Wi-Fi router and so on, they are all embedded applications. Now, and these embedded applications are usually based on two different platforms, software or hardware, or a mixture of them. For me, hardware means that you have a piece of hardware, really like a FPGA or ASIC that you have built or constructed, yeah, here. And the software for me doesn't mean that actually the program which runs on your personal computer. That actually is not software for me. Yeah, for me, the embedded software means that a microcontroller might be small, might be a bit large, that actually performs some operations sequentially. It's like ARM processor, like RISC-V, like much simpler processors from other companies like Atmel and so on. And then I actually work mainly here and make myself busy with challenges that we have when we want to implement or realize these cryptographic primitives, that they are secure with respect to theoretical analysis, but we want to implement them in either hardware or software or mixture of them. And then what are the challenges here? One of the challenges that we do, and I'm making myself busy with, is physical attacks. Before explaining the physical attacks, I would like to agree with some definitions with you. One of them is cryptographic device or crypto device. For me, cryptographic device means a piece of hardware or software, means that there's again ASIC, FPGA, or an embedded microprocessor which performs the crypto, which performs the cryptographic primitives. And then, of course, there is a key inside which is embedded, and then you can talk to this device. Means that you can see there's an oracle that you send something to this device and receive the results back. Of course, you have some handshaking and so on. And this for me means a cryptographic device. And what we do in physical attacks, or a particular branch of physical attacks is called passive physical attacks, actually those that we are trying to recover the key which is inside the device, recover this key which is inside the device using some information that you have heard probably. I mean, timing information, the number of clock cycles that the device needs to perform an operation, or amount of power consumption of the device using some oscilloscope that you can measure this over the time, means an instantaneous power consumption, or you put a probe at the top of the chip and then you measure the power consumption locally using electromagnetic probe, which is very, very similar to power consumption measurements. And then based on all of this, you try to recover the key which is stored inside the device. I guess you have heard a lot of examples before and heard about what side channel attacks can do. And here I have a concrete example for you that you can probably recognize this logo of the chip, which is the iPhone, pretty old iPhone. And then it's the A4 microprocessor. And then these devices have an AES embedded inside. It has hardware. One AES design, which actually embedded into this platform, which is a microprocessor, and also a lot of other devices which are close to the microprocessor and communicate with it. And then what we have done, we have tried to put an electromagnetic probe that you see is a very large probe at the top of the chip, and recover the key which is actually dedicated to this device. Because I don't know how much you are into the specification of the Apple devices. Each device has a key inside, a unique key, a unique secret key for the AES, AES 256, and also every category, every family of the devices also has a particular key. It means that you have two different keys for every device. One is for the family, and another one is dedicated and unique for your mobile phone, or Apple device. If you have two devices from the same family, both have the same key or family key, and both do not have the same user key. The user key will be different. And then what you can do, again, I don't know how much you know, that if actually you can try to recover the pin of the iPhone completely without using any electromagnetic attack or any power of any side channel attacks. It means that you can just use the device and search for the pin in an exhaustive search way. And then you can see here, if you have just 4-digit pin, and then you just need 13 minutes to recover the key. Of course, this is dedicated to the family of this chip. This is the A4, and this has some problems. And then based on that, if you have an old iPhone, for example, iPhone 4S, I think nobody is using it at the moment here in the room. But if you are using it, and if you have a digit of 4-digit pin, then it just required only 13 minutes to recover your pin. Of course, completely without any side channel attacks. Then what we can do, we can recover the key of the AES here, and then run all these attacks offline using, for example, some GPUs, and then accelerate this process, this exhaustive search, and then recover the key much faster. And then you can see, if you have, for example, 10-digit pin, then it will take 25 years to recover the key using the iPhone by itself. But then you may decrease this, of course, using more GPUs, and then linearly the time that you need to recover the key will be decreased. Good. This was just one example of the attacks. And then the question is how to protect. This is something that I made again. I've worked on it around or I started working on it around 8 years ago, and working on the different aspects, how we can really provide security for the devices against these attacks. And then the first thing which comes to the mind, which actually was not invented but remarked in roughly 20 years ago, is about randomization. It means that let's say you can measure the power consumption, but I randomize the power traces, and then you are not able to really recover the traces. This is absolutely fine in practice. I mean, in industry. And if you get some devices that they claim side channel security in the market, most of them actually do some randomization. And then, of course, by this randomization, they reduce the SNR, which is signal to noise ratio, and then the amount of information that you can recover will be decreased. But the problem is, with these schemes, you don't have any security proofs. You cannot prove the security of your implementation. You cannot say, okay, up to 1 million traces, my device is secure. this is okay using your device and using your setup, but it doesn't mean that if somebody else is using another setup would exactly need, again, 1 million traces to perform the attack. May need more or may need less. You cannot prove the security at all. For that reason, another branch of the protection is known, which is called masking. The masking is actually coming from domain, which is called secret sharing schemes. And then another one, or the most important one, the most important secret sharing scheme, which is used in the context of sidechain attacks, is called Boolean secret sharing. The good thing about masking is that you can define an adversary model and then you can prove the security of your implementation. I will show you how. And then the fact is, usually if you implement masking correctly, then it will be completely, or the level of security will be completely independent of your measurement setup. It means that if you prove that, okay, this device cannot be attacked under this adversary model, then it doesn't matter how you measure it, or how you implement this. Okay, let's see together with the Boolean secret sharing scheme. The thing is, if you have a secret X and you want to share it with two bodies, you want to give X1 and X2 to do different bodies or parties, and then they should not get any information about X individually. It means that if you give X1 to someone who should not be able to get any information about X, and if you give only X2 to someone else, that person should not be able to get also information about X. But if you give both of them to someone, then they get information fully about X. How you realize it in Boolean secret sharing? It's easy. You can say, okay, I select X2 completely randomly. M is a random value. And of course, it should follow a uniform distribution, which means that you selected X or X2 or M from a uniform distribution at random, and then say, okay, X2 equals M, and then you calculate X1 as X or M, and then you just say, yeah, XOR of them is X, but if you give X1 to someone, should not get any information about X as long as M follows a uniform distribution. And of course, if you give X2 to someone, it's the person gets only the random value and does not get any information. This is the concept behind Boolean secret sharing, and of course you can extend this. You can say I have X1, X2, X3, and so on. And then you select X2 random, X3 also random, X4 random, and then the sum of them will be the value that you put instead of M here, and then you calculate X. Then, okay, we have done this. That's good job, but how can we use this? For which reason we did this? Because we want to perform the operation. It means that this person who got the X1 can run some operations on X1, and that person who got the X2 also can run an operation on X2. For example, you have linear function, of course, in a linear in the domain of let's say binary linear function. You can define it as, okay, f of x, x or z is a f of x, x or f of z. Is that if we define the linear function like this, then this is actually transparent to this Boolean secret sharing scheme, and then you can easily say, I can actually apply this f that I want to apply on x. Instead of applying f on x, that x is secret, then I apply f on x1 and also apply f on x2 individually. Then it means that I apply actually f on x. It means that I can here at any point in time get the output of this one and output of this, and again XOR them, and I get this guy. This is good. The work is done, the job is done, but it's only for linear function. If you have a cryptographic operation, of course, cryptographic algorithms are not only linear. If it's fully linear, then of course it will be easily broken. Then you need to have some linear operations as well inside your operation or inside your cryptographic primitive. Then how can we apply this a nonlinear function? This is actually the difficulty because this doesn't hold anymore. If you have a nonlinear function, you cannot apply it on x1 and x2 individually and say, hey, I have applied this nonlinear function on x. This, of course, doesn't work. So for that reason, if you see many papers on masking, all of them are actually dealing with this problem, most of them. How can we apply a linear or Boolean secret sharing scheme on some operations, on some functions which are not linear? For example, the S boxes of some symmetric cryptographic schemes like AES, for example. What you can do, you can say, hey, if you know AES, I hope that you have heard about the AES, and the AES has an S-box, no? And this S-box is nonlinear. And then you say, what you can do instead of a S-box that you want to perform an X, what you can do, I build a larger function which receives X1. If you remember, this was X1, and this is also receive X2. Then instead of, if you remember again, AES has an 8-bit S-box, then you have 16-bit as the input to this function, and then you get 8-bit output, which is the masked version of a S-box output. Here is the S-box input, and you mask the input, not like this, and then you want to get the S-box output, which is again masked with another M prime. And M prime can be, for example, a function of M, or can be also additionally given to this. This will be a large lookup table. S-box, AES S-box is 8-bit, 2 to the 8 cases, 256. Now you have 16 inputs. And the problem is, even you implement this in software, you can run it as lookup table, but in hardware, it will be also super, super hard, because it will be large, fully combinational circuit. And then the problem is here that this is, if you implement in hardware, if you implement this by some gates, some combinational circuits, some AND, XOR, and so on gates, then it will be fully combinational. And then this is a function which receives X1 and X2 together. You remember, we wanted to have, if I back to here, we want to run operation on X1 and only on X2. Now I have an operation which receives both X1 and X2. Which receives both on X1 and X2, and I cannot guarantee that this device actually does not leak any information about X, because it receives both shares. Then some people actually many years ago said, the reason for that leakage, if you give X1 and X2 to this function, because of glitches. You may have heard about the glitches. Glitches are making masking actually not working correctly. I mean, they destroy the mask. I mean, it's up to some extent is correct, but even if you have a circuit which doesn't have any glitch at all, and this actually receives both shares, you cannot guarantee that this has this doesn't have a leakage about X. Glitches are actually not the only reason, but they amplify the things. Then, because of that, a couple of systematic schemes have been developed. One of them you may have heard about, a TI, or threshold implementation, which can provide the security with a provable or some proofs for the security. Let's see how the TI works. For that reason, to explain you how the TI works, I would like to give you an example based on just a S-box. Suppose that you have a S-box. It doesn't matter how many bits. I mean, suppose 4 bits is S-box X, and S-box output is Y, again 4 bits. Suppose it's a bijection, as an example. And then you want to represent X with 3 shares, X1, X2, X3, in a way that XOR of them is X. And then you want to build some other function instead of this S-box in a way that they produce also Y1, Y2, and Y3. If you XOR them, you should get Y. This is what you want to do. But the interesting thing is what you want to do. I mean, if you look at here, F1 receives X2 and X3, it doesn't receive X1. Now, it means that this guy, if you remember again, the Boolean secret sharing scheme, F1 does not gain information about X, right? Because X1 is missing for F1. Then the leakage of this will be completely independent of X. And F2 receives both shares of X1 and X3. It doesn't receive X2. Again, X2 is missing here, and then the leakage of F2 will be completely independent of X. The same for F3. And then if you look at this an average, which means the average, looking at the average of the power consumption based on one X, for example, you put X equals 0. And of course, there are many different ways to represent X equals 0 with randomly distributed X1, X2, and X3. And then you look at the average of the power consumption of this, and again, change X to X equals 1, and again, go for all possible values of X1 and X2 and X3. And then again, average of the power consumption. This average power consumption should be independent of X. Means that you already reached what you wanted. You want to say, okay, the then power consumption will be completely independent of the value that is processed. But how do we achieve this? I mean, this is simple in saying that F1, F2, F3 should be like this. But I give you an example here. Suppose here X input is called A, B, C, D, and Y is called E, F, G, H. Now, this is the bits of this, because as I said, it's 4-bit SBox. And then I just write here one coordinate function of this SBox, which receives this 4 bits input and generate one output bit. Yeah. Then you have 4 of these coordinate functions, one for E, one for F, one for G, and one for H. And then here I wrote here the A and F algebraic normal form of E based on input A, B, C, X, or D. And then what I want to do, as I said here, X is represented by 3 shares, then it will be the same for A, the same for B, and also other inputs in a bitwise way. Yeah, means that A represented by A1, X or A2 and A3, B also with B1, X or B2, B3, the same for C and D. And then if you write all the terms, you end up with these terms. No? And then you see that E actually is one of the bits of the Y, means that I just need to divide these terms into 3 groups, put some of them in F1, some of them in F2, and some others or the rest in F3. Yeah, then it means that actually I reach exactly what I want. Yeah, but the point is, I look at here, F1 receives everything except X1, means that I cannot put A1 here in F1. Yeah, but I can put A2, I can put A3. I cannot put a B1, B3, B1, B1, C1, because both of them have index 1. Here, I cannot put B1, C2 into F1 because it has index 1, and so on. Yeah, then I can easily say, yeah, these terms, which are B2, C3, they can only go to F1. Yeah, the terms which have B3, C1, 1 and 3, they go only to F2. Then this is clear at where they go, but some other terms, for example, A2, I can put A2 in F1. I can also put A2 in F3. But not in X2, not in F2 here, right? And then this is actually, I can say the job is done here like this. Then you build something which is actually secure, and the leakage will be independent of X. One problem that we have here is uniformity. What is the uniformity? If you remember, I said if you select a random value as for X2 and random value for X3, and just calculate X1 based on here, yeah, you can say X1 equals X or X2 and X3. Yeah? And then if you remember, I said the distribution of these random values should be uniform, right? They should be taken from a uniform distribution at random. And then if you consider here Y2, Y1, Y2, Y3 are the output of this function, which are again masked, a shared representation of Y, they will be given to another functions in the next part of the cipher. This is just the SBox, right? And then they should also follow a uniform distribution. Means that you should be able to say that this Y1, Y2, Y3 is a uniform shared representation of Y. Otherwise, the function which comes after this SBox leaks already information. Yeah? For that reason, you need to achieve the uniformity. And uniformity here means that if a SBox is a bijection, then you can see this large function as receiving one large input, which is 3 times X, and 3 times Y is the output. Then this large function should be a bijection. Means that it should provide a uniformity. Means that for all possible inputs that you give here, you should get all possible outputs of the output. Otherwise, you do not fulfill the uniformity, and then the next function will leak. How to define this and how to find this is that this part that we have freedom. I mean, A2, you can put, as I said, into F1 and to F3. And if you change the position of this term, then it already changes the uniformity for you. Now, then it is not easy to build something like this, which is fully uniform. And you have to check or change the position of these terms, and again check whether the design is uniform or not. Yeah, you see the difficulty here. Another point which is difficult, you can see here, you can't actually distribute this term easily into F1, F2, and F3, but there is a reason for that. Because the function is just quadratic. Yeah? The algebraic degree of the function is 2. If you have algebraic degree 3, for example, if you have B, C, D, then you will end up with a term like B1, C2, and D3. Means that all 3 indices are there, And then you cannot actually put that term in any of this. Yeah? But then, because you don't have any function which depends on all shares, then you need to increase the number of shares. Means that instead of 3 shares, then you will need 4 shares if your function is cubic, if the algebraic degree is 3. And so on. Then it will become hard. Yeah, I mean, if you know the AESS box, do you know the algebraic degree of the AESS box? Does anybody know? Oh, it's 7. Yeah? Algebraic degree of the AESS box is 7. Then you need 8 shares here at least. It will be extremely large. Or you decompose the function in 2 parts, and each part should have a lower algebraic degree. I mean, it's possible to decompose the AESS box into 2 cubic functions, and each of them shared with 3 shares, and you go forward. This is super hard. Yeah, this is not that easy. For every algorithm, you should sit down and check whether you can do it or not. Another part. I explained this for you. The process that we do, the process that we build masked circuits is at the moment like this, that you have an unprotected implementation. For example, you are working in a company, or you ask your colleague or someone else to say, okay, I have this unprotected implementation of the AES. For example, you write it in behavioral level of Verilog or VHDL or system Verilog. And then somebody sits down and then try to build a manual design like what I explained. This will be not easy, because if you change it, for example, AES to another cipher, you have to do everything again from scratch. And it's not as straightforward. It's super based on experience. I mean, after many years of experience, you may still make mistake. And then it's at algorithmic level. Yeah, I mean, you need to do it, for example, for the S-box, the AES box or S-box of the other ciphers. And then, as I said, it's highly prone to error and defects. And then at the end, the colleague or yourself, you come up with a side-channel protected implementation, again in a behavioral level, which is, for example, Verilog or VHDL or any other language. This is the process that we do. But what is the problem is what we have in TI or threshold implementation, all these schemes, is the non-composability. Means that you build the AESS box and you are sure that this is absolutely secure. You like this. And then somebody use this AESS box that you build, which is absolutely secure and uniform, in this way. Say, okay, I have an algorithm. The X is coming here, and then it goes to a box, and then the input and output are XORed together. If you build it like this, and then you build the TI, and you know that it's absolutely uniform here, if you do the XOR here, it's not guaranteed that this output is uniform. It's not guaranteed anymore, because means that you have to sit down again and check whether this is fully uniform. And this is the problem of non-composability. It means that you build something and it's standalone secure, but it depends how you use it in your implementation. If you know exactly what to follow, you may end up with a secure system or secure design, but not necessarily. Now, this is highly dependent on the expertise of the people. For that reason, some notions of composability have been defined. Means that let's build something which we call it a gadget, composable hardware gadget, that it's secure by itself. I mean, standalone is secure, but also it fulfills some other criteria. With this, you can compose it. It means that when you compose it, it doesn't, or it actually fulfills some criteria. Then the circuit which is composed based on this gadget will be secure at the end. Then you can prove the security of the system if the system is fully based on only these composable gadgets. It means that it's only composed of these composable gadgets. Then, if you have these gadgets, what we can do at the moment is that instead of going through this direction of manual design, you get this unprotected implementation, again, behavioral level, Verilog or VHDL, and then you synthesize this. I mean, synthesizer, I don't know whether you know the synthesizer, is a design that you give the hardware implementation to the program, which provides for you the netlist of the design based on a library. For example, you say, I have AND gate, OR gate, XOR gate, and so on. Then it builds the netlist of your circuit based on the fundamental gates that you have inside your library. And then what we can do, we build a tool for that, which is called AGEMA, Automated Generation of Mask Hardware. Means that you give this netlist to this program or this tool, and then it identifies which part or which module should be secured, and then it replaces these gates with the composable gadgets, and then the user can define the level of the security, the order of the security, and also some say, okay, I want a small design or I want a very fast design, and so on. Yeah? And then at the end, it provides a functional prototype implementation, again, based on a net list. It's not a behavioral level anymore. And it's free of heuristics, and you can prove the security, and it's also free of any engineering failure. And then it's also available on GitHub. Yeah? There are some requirements for AGEMA. You need to have some composable security. I explained fully the composable security. The most important notion at the moment, or more, let's say, effective notion that we have at the moment is called PINI. Some people call it PINI. It's probe isolation non-interference. Means that you should fulfill some criteria to be to say okay, my design is PINI, and then if it's PINI, you can easily compose it to build again a secure circuit. Usually at the moment, PINI gadgets are just for essential gates. Means that you have just 2 input AND gate, 2 input OR gate, and so on, and XOR, and then you can build the PINI or PINI gadgets of this. The examples of called HPC2 or hardware private circuit 2 and HPC3 hardware private circuit 3. I will show one of them as an example later, but keep in your mind that this will be HPC2 and HPC3. And now let's see how AGEMA actually works. AGEMA models the given circuit based on a Mealy machine. I don't know if you have studied electrical engineering or computer science or computer engineering, you may have heard the meaning of the Mealy machine and Moore machines. It's like this, that you have a primary input here, primary input given to the combinational circuit, and then you can put all registers here at each let's say in a range, and then this combinational circuit receives the primary input and also the output of the register in a loop, and then here the output is taken from the combinational circuit. Now, this is the Mealy machine generally. Means that the AGEMA models the given circuit, the given netlist using this model, and then as an example, here, for example, is the given netlist. Yeah? And then what is important in AGEMA, you need to define, okay, which primary inputs should be masked. Yeah? And then the rest is taken care by AGEMA. For example, here I say I1 should be the mask. This is the only input that I want to give to the circuit, this X that we have seen together. Yeah, this should be represented in a shared way, and then AGEMA actually propagates this to here and say this gate should be masked, and then the output of this should be also masked. The output of the gate number 2 should be masked, and then this register should be masked, and then loop back, and then this gate, the gate number 1 will be masked, and so on. And if you continue here, you end up in this loop. Then nothing else is added, and then afterwards it's called secure zone at the top, and bottom is called the normal zone. Yeah? Now, we have this circuit that we identified by AGEMA, the green one, the red one, the secure zone and normal zone, and this is the circuit that AGEMA builds based on this. Yeah? It replaces this gate number 1 with this HPC2 NAND gate. This is a NAND gate. This is an OR with HPC2 OR, and the XOR is very simple. And in PINI, this is also a gadget. And then you see here the HPC gadget has some register stages inside. Unfortunately, at the moment, we have to put some registers inside the circuit to fulfill the PINI or PINI requirements. Without this register stage, we are not able to build any composable gadgets at the moment. Yeah? Then, if you do this, then the circuit actually doesn't work like before. Because here you had a fully combinatorial circuit, you put some register in between these gates. Then AGEMA understands, okay, 1, 2, 3, 4 stages of registers you have. This input should be also synchronized with the other input, and put 2 registers are added here. 2 registers are added here, and then in total, 4 registers should be added also here to synchronize this guy with this register. Now, and then at the end, the circuit will work exactly similar to the other one, but of course with the latency. 4 times higher latency. Here, for every 1 clock cycle of this, you need here 5 clock cycles. Then this is a super simple example, but can see the full AES, not only the SPOCs. The full AES cipher is given like this to AGEMA, and then it's processed like this, and everything will be fine, and then you can prove the security. This is a general procedure. I don't want to give or explain you all the details, but the unprotected implementation is given here and some attributes for the primary inputs. And then there are different schemes that you can select. And then finally, the mask design is generated. Yeah. Then I provided one demo for you. I mean, you may ask, yeah, how does it look like, how it works? Here is the AES. You can see AES design. It's the net list. And then here I give some attribute to the input. You see plain text is 128-bit and the key is also 128-bit. I say here it should be masked. Here the key should be also masked. This is my clock signal and this is the reset signal that I have. Now this is just attributes that you give. And then I have it here. For example, you can see I have written this before that you give the library file to this, and then this is the actually, this is what you can see here. The AES file is exactly this file that I give here, and then say the name of the module is the AES, because you see here is the AES, no? The name of the module. And then say naive, because there are different methods that we can recover. And then I say, hey, I say here HPC3, no, HPC2 I want to build. And then it takes some time, it reads the file, and it generates the output. Now, I mean, I show you here the result. Here, now this guy is generated. You can see here the plain text now changed to plain text S0, share 0, and share 1. And here the same for the ciphertext and ciphertext. Yeah, ciphertext is also changed to this, and then it considers the entire gates and something that is inside the circuit. It's super easy to build actually larger circuit. Yeah, security order was 1, now security order 2. It builds a larger circuit now with 3 shares instead of 2 shares. Now this file is generated. And then you can see here, now we have plain text S0, plain text S1, and plain text S2. The same for the key, because we asked for the key and plain text to be masked. Even now I can say, I don't want the key to be masked. I think it's constant and constant. And then I can run it again, security order 2. And this file is updated now. You can see plain text is shared, but the key is not shared anymore. Yeah, but of course, it's propagated to everything, and you see the ciphertext is still shared. It's considered that this the AES cipher fully in a it's the AES round-based implementation. It means there are 20 instances of the S-box. Now this is a super large circuit. Yeah, it was never possible to build, for example, the sargent protected version of the AES with some just lines in a couple of seconds. Yeah, I mean, you can increase this, go to the 3rd order, to the 4th order, and even you have a larger design or a smaller design, it doesn't matter. Yeah, all of them work like this. Good. This is what I explained you, and about the requirements I already explained about the efficiency. Yeah, it's clear for us that this is provable secure. You know, it means that you can, as long as the gadgets that you use are tiny, then it will also provide a provable security, and you can extend it to any arbitrary order easily. But the problem is that it's not as efficient as manually crafted designs. If you are an engineer and you know exactly what you are doing, yeah, and you very, very likely build something which is more efficient compared to what a gamer can do. I mean, with the same security level, if you use, for example, the composable gadgets, everything will be fine. Yeah, and then the point for us is that any engineer, even without any expertise in the side channel domain, can make provably secure designs, which are actually secure in practice as well. Yeah? Good. This is one example of the HPC3 gadget. It's you know, you just have AND gate with 3 inputs. Now this is supposed that it's just a part of the gadgets that you have, which HPC3, which is a low latency. You have registers here in between. I mean, X and Y are two inputs of the gadgets. Now you represent X with X0 and X1, and Y with Y0 and Y1, and these R that you see are just random value that you have to give. Yeah, and then Z0 and Z1 are provided as the output of the gadget. Now, then imagine that you have a just AND gate with 2 inputs. Now, instead of that, you have that large circuit to to build as a gadget for the AND gate. Now, for that reason, of course, the resulting circuit will be large, but you can prove its security. Good. The last topic that I want to shortly go through is about how do we actually then examine the security of the implementation. Yeah, I mean, suppose that you build a circuit which is, you say, is secure, provably secure. If you do handmade design or manually crafted design, how do you evaluate the security of such design? The problem is that if you want to just run the attacks, it's not that easy. Yeah? I mean, you can have DPA or differential power analysis, correlation power analysis, mutual information analysis, many other attack vectors, and many different intermediate values that you can select, and many different leakage models that you can select, and you can never be exhaustive. You know, you can never cover all of this and say, hey, I have checked all the attack vectors and I'm pretty sure that my device is secure. Yeah? This never happens. First of all, you can never be exhaustive, and then somebody can come and say, hey, I performed the attack using another method, another model that you have not considered, and that your device is actually can be broken. Yeah? For that reason, there are schemes that they are called leakage assessment, that you measure the power consumption here or electromagnetic radiation, and then you do some tests. They're called statistical tests. I'm pretty sure you heard about the student t-test, that you have two sets of measurements or two sets of samples, not necessarily in side channel domains, some just samples from the distributions or from different populations, and then you want to check whether these samples are taken from different populations or not. And then statistical tests like t-test or like chi-square test can give you a level of confidence to say, hey, with which level of confidence you can say that these two samples or these two groups are taken from different populations. Yeah? But this is again a bit hard to do, and some particularly when you make an ASIC design, you not only an FPGA test, you have to build the ASIC and then bring it to the lab and then check it. Yeah, what we do and many people try to do is to do pre-silicon evaluation. Means that you build again the protect implementation. Here you see hardware protect implementation and behavioral level. You synthesize it, build again the netlist, and then you give this netlist to the verification tools that we constructed. They are called Silver and also ProLead. Now I will explain what they are and how you can use them. The point is it's actually free of any false negative, because here in the experiments, you may measure the partial measurements with one setup, and then you may say, hey, it doesn't have any leakage. Yeah. And then somebody else bring it to another setup, which is more advanced and better quality. It may actually recover or exploit the leakage. Yeah, this actually should not happen here when you use our tools or similar tools, and it's completely free of any heuristics, and also it's independent of any experimental analysis, and it's also available on GitHub. You can try them, but I will explain you how they are. Most, as you see here, I mean, get back here. Both of these schemes are based on probing security, because there are many tools in the market. I mean, the scientific market, and that they actually also industrial market existed. These tools that they can simulate the power consumption. That you build this and give this netlist to the implementation or to these tools that they have, and then they estimate the amount of power consumption, and based on this result, simulated power consumption, then run these tests. This t-test and chi-square test. What we do here is that the scheme is based on probing security model, and you may ask, what is a probing security model? The idea is that if you have a circuit like this, and you need to put the probe on different part of the circuit, and for example, you say first order security, then I put the probe here, and probe here, and probe here, and here, and every different places, single probe I put, and these observations that I have about the intermediate values should be completely independent of any circuit. Now, any circuit, completely independent of any circuit should be. Yeah. Then you should not be able to understand any information about the circuit if you put just one probe. It's similar to that circuit sharing scheme. Yeah. If you have only X1, you should not get any information. If you have only X2, you should not get any information. This is the same. But the problem in hardware is that this doesn't cover all the problems. I mean, if you remember, we talk about the glitches. I mean, this is called the glitches are amplifying the things. And it's called we have another model which is also partially developed in TU Darmstadt, Yeah, robust probing model means that you put the probe here at the output of this gate. This actually propagates backwards to the circuit based on the glitches. Yeah, it means that, okay, you say this propagates to this input, which is the primary input of the circuit. This propagates also to this register, which is also the input of this combinatorial circuit, also to this, based on the glitches. Yeah, but then another point that we have is the transitions. Yeah, means that the input of the circuit is only not affecting its power consumption. The previous input of this circuit also affects some information, or affects the amount of power consumption. Then we have to consider the previous values or the next values which are coming to these registers. Then this probe that you have here will be also propagated to the probe which is here, which is also here. But of course, it's not propagated anymore to B, C, and D. Yeah, this means that one probe you have here, and then you have to look at the distribution which is observed by these 5 probes and say whether you get any information about the circuit or not. It's not only one probe putting it. This probe is propagated. And then if your circuit is secure under this model, which is pretty conservative model, yeah, then it doesn't matter how you really implement this, whether the power consumption is higher, lower, or your setup is good or not, or bad to measure, then you are actually, you can easily put a finger on it and say, okay, this is provably secure. Yeah? And this is exactly what our tools do. I mean, Silver and ProLead, you may say, why? We have 2 tools for that. The Silver actually exhaustively checks. Exhaustively checks for all possible unmasked inputs of the circuit. If you remember this as box that we checked, the X was the input and Y was the output. If you remember that, guy, then we have to go through all possible values of unmasked X. And then it checks, or Silver checks, whether the distribution which is observed by the probes will be completely independent of all possible values of X. Yeah? And it to calculate or build the probabilities, to estimate the probabilities, it builds an ROBDD. It's called reduced and ordered BDD, binary decision diagram. Yeah, and then based on that, it can more easily calculate or estimate the probabilities. And this BDD is built based on this net list that we give to the device or the program. Then the problem is if the net list is large, if you have full AES, you can never build a BDD or ROBDD. Then Silver is restricted to just very, very small circuits. But the solution that we have instead of Silver is ProLead, is another tool which performs roughly the same, but it's not exhaustive. Yeah, you define the number of different inputs that you want to check. For example, it's similar to a statistical test. It's called G-test. If you have heard about a statistical G-test, it's another version of, again, chi-square test. Yeah, and again, it's for different inputs which are given. For example, X, 2 different X, I mean fixed values, or 2 different inputs like this, that the X is a fixed value, X equals 0, and all other values of the X which are completely random. And then it checks whether the distributions which are observed by these probes will be completely independent of these inputs that you have made into groups. One group is this fixed value, and another group is completely random inputs. It might be a bit scary and to understand if you have not done anything in the probing security and such an analysis. For that reason, I would love to show you something here. Something that you can easily build. You can say, hey, I have X0 and X1 and Y0 and Y1. And I want to build actually as AND gate. Yeah, I want to build something like this. And then what you can do in theory is that you say, hey, these 2 are going to AND gate, and these 2 are also going to an AND gate. And then you build another AND gate with X1, Y1, another AND gate with here X0 and Y0. Yeah, with this you already built all terms. Here you build X0, Y0 plus X0, Y1 plus X1, Y0 and X1, Y1. Now you build all the terms, and then what you have to do is you have a random value, which we XOR with this, and then you put register here. And then you XOR the result. And this we call it Z0, this we call it Z1. It's actually the implementation of the DOM, if you have heard domain-oriented masking of this AND gate. Yeah, this is a secure AND gate. I mean, it's not necessarily fully composable, but this is a secure implementation of the AND gate using 2 shares. Yeah, and then I will show you now here how to check this with ProLead. Here is the design. I mean, I already have prepared these AND gates for you. Yeah, and these XOR gates, which were these XORs, yeah, with a random value, and these 4 flip-flops that we have also seen, these 4 flip-flops, and 2 XOR gates, which are here. No? And now I built a config file, how to check this design. I mean, of course, I cannot go through all the details, but now here I already prepared this. And then if you run this, it tells you, hey, everything is okay. Yeah, you can see it here, everything is okay. And then how many traces and so on, everything is written here. I mean, we have used, I don't know, 3 million traces up to now. Now, I mean, if you are an engineer and then you, for example, you made a mistake. Yeah, I mean, you remove one of these registers or you forgot to put one of these registers. And I don't know whether you know Verilog, you might say assign, and then I remove this register and say the output of this register is the input of its, I mean, this is the same as input, Q4. Yeah, it means that I completely remove this register. And then again, I run the test, the same test, you will see directly it recognizes the leakage for you. Similar to this, I mean, you can give it a full AES, and of course it takes longer, and then you may need to use some servers with more power or some computing power to be able to run this. These are the result of all these works that we have done. I mean, roughly 4 works in the areas of building the circuits in an automated way, and 2 works, as I said, about Silver and ProLead, and all of the results are actually available on GitHub in addition to the papers. One more thing, this is the last slide, I promise. I mean, I run out of time already. For example, the importance of this, you may say, hey, companies are actually doing this by themselves. Yeah, by hiring some experts to build the mask implementation, the secure implementation of the AES and other ciphers. Nowadays, the trend is to build implementations or secure implementation of post-quantum crypto schemes. Yeah, and for example, this is one activity initiated by NIST and IST about mask circuits for block ciphers. Of course, this is just for the symmetric block ciphers. Yeah, I mean, that there was some activities. It's not followed fully at the moment, but the idea was to build some concept and also standardize some concept and implementation to say how to build really the mask circuits for ciphers like the AES. Good, and with this, I come to the end. Thanks so much for your attention. I hope you got some information, and then in the future, if you want to work on this sergeant security or masking, then you have some links to follow.